Good. And let me do the share screen as usual. And I'll have to set this up, which should work without trouble if we are lucky. All right, let's see here. You lock this in. Maybe I can enlarge it. Okay. All right, so the display I've got up here is a summary of some of the stuff we did in the last lecture. This is regarding hyperfine effects in atoms, which I'll remind you concern the influence of the higher order electric and magnetic multipole moments of the nucleus on the atomic electron and generally on the atomic structure. So if we think of, so to begin with a completely classical picture, if we think of the nucleus here, where this is this blob here represents the nucleus, as a region of space that contains a charge and current distribution, then at some field point X, which is out here, I've drawn it as if it's outside the nucleus, we can compute the electric and magnetic fields, or really we'll work with the potentials, the scalar potential and the vector potential at the field point. And if you do that, you can expand them in the multipole expansion. For example, the scalar potential has the monopole, dipole, and quadrupole terms. The monopole term is the usual Coulomb potential, as if all the charge were concentrated at the center. And then the other higher order moments give you information about how the charge is actually distributed around that center. The D here is a dipole moment vector. Well, the Q is the total charge, lowercase q. The D is a dipole moment vector, and capital Qij is the quadrupole moment tensor. These are defined in terms of moments of the charge distribution. Q is just the total charge. The dipole moment vector is the charge weighted position vector, and Qij, the quadrupole moment tensor in Cartesian language, is the charge weighted tensor that you see here, 3xi(xj) minus r squared delta ij, something that occurs a lot in this discussion here of fine structure. So I've given an abbreviation, call it Tij. The T just stands for tensor. That's the one that occurs in this problem. And you can see that it's a symmetric and traceless tensor, meaning that it corresponds to a k equals 2 irreducible tensor operator when we classify things in that manner. Likewise, the magnetic field at the field point X has a multipole expansion. The monopole term is 0 because there's no magnetic monopoles. The dipole term is given by mu cross x over r cubed, where mu is the magnetic dipole vector. It's described as it's another integral over the source distribution. It's the integral of basically of the position vector crossed into the current integrated to the source. These integrals that I've got here are really taken over the source distribution. If you want to distinguish the variable of integration over the source distribution from the field point X, you might want to put a prime in here like this on all of these integrals like that. That's sometimes a useful notation to keep track of what the different X's are. All right. Now this is all classical, and it just comes out of Griffith's books, basically. The quantities Q, D, Qij, and mu that appear here are just ordinary C numbers, which characterize the charge distribution. If you think of this charge distribution as due to a nucleus, of course, you can rotate the nucleus and move it around. And if you do, you rotate these vectors, the dipole moment vectors get rotated by the rotation, they change direction, and the tensor gets also rotated too in the manner in which tensors transform under classical rotations. Whereas the charge, total charge Q, of course, is invariant under the orientation. It's really a scalar. Now these quantities, as I say, are just C number quantities, but they're obviously quantities that refer to or relate to the nucleus itself. And so they are, classically speaking, they're observables. They're observables. In fact, they're dynamical variables because they've evolved in time. Certainly D and mu do, because the nucleus precesses in the magnetic field. Now, by the postulates of quantum mechanics, those must be associated with operators which act on the nuclear Hilbert space. So let's look at that. The nuclear Hilbert space, we know what this is because we've been through this before. It's a single irreducible subspace under rotations, which I call E nucleus here. It has an angular momentum vector, which we denote by I, This is otherwise the same thing as the nuclear spin. This notation distinguishes it from the electron spin, which we call S. So I is the nuclear spin, S is the electron spin. The standard angular momentum basis inside the nuclear Hilbert space is just IMI, where the I magnetic quantum number runs from minus I to plus I. And the operator I squared, as usual in quantum mechanics, has an eigenvalue, which is I times I plus 1 h bar squared, where lowercase I is the what we call the spin. You know, the spin is a scalar characteristic, the spin of the nucleus. All right. So these various moments and get promoted into operators on the nuclear Hilbert space.
We're ignoring the volume of the nucleus by doing this?
Excuse me?
Are we ignoring the volume of the nucleus by doing this?
No, because these integrals are taken over the volume of the nucleus. These are integrals over the source distribution, the rho and the j, and they only extend out to the radius of the nucleus. So that's the limit of these. If you want me to, I can put little v's in here to indicate that this is taken over the volume of integration of the nucleus.
Right. I just meant when we start talking about the observables, you know, because we're not taking into account like the spatial degrees of freedom of the nucleus.
Well, in a sense, we are the spatial degrees of the freedom of the nucleus, and well, let's see. What do you mean by this? Oh, you mean the center of mass? Is that what you mean?
Yeah, I just mean like the fact.
These integrals are taken with respect to the center of mass. I didn't say that, but that's what they are. So they're independent of the center of mass of the nucleus.
Okay, thank you.
Okay. Of course, the center of the mass of the nucleus has its own dynamics. I mean, it gets accelerated and so on. All right. Now, all right. So that's the basic setup then of the classical multipole moments. The multipole moments are related to integers that I call k here. The Greek and Latin prefixes mono, di, quadro, and octo refer to powers of 2, 2 to the 0, 2 to the 1, 2 to the square, 2 cubed, and so on, 1, 2, 4, and 8. And the logarithm of those, as to say, the exponent is either 0, 1, 2, or 3. And these exponents correspond to this k value here, which is the exponent, corresponds to the index or the rank of the irreducible tensor operators, which these moment operators become when you quantize them and regard them as operators acting in the nuclear Hilbert space. So for example, Q, which is a k equals 0, is a scalar operator. It means just a multiple of the identity. On a single irreducible subspace, any scalar operator is a multiple of the identity. And that just means it's a characteristic of the nucleus, which we knew already anyway. That's what the charge is. On the other hand, the electric and magnetic dipole moment vectors are, after all, vectors. And so they transform into rotations in a certain way. That's the definition of a vector operator. And that means that they're actually k equals 1 irreducible tensor operators. The quadrupole moment tensor, on the other hand, is a k equals 2, and this carries on through. I won't prove this, but this is a fact about these multipole moments. They're associated with a rank of an irreducible tensor operator. I'll remind you that on a single irreducible subspace, apart from a multiplicative constant, there is precisely one scalar, one vector, one k equals 2 irreducible tensor operator, and so on. And so all of these things that appear here are proportional to any standard such scalar, vector, k equals 2 irreducible tensor operator, etc. And I think you had a homework problem on the quadrupole moment, and the d and the mu is also similar. That's just a way of saying that d and mu are proportional to the nuclear spin I, because that's the vector operator. All right, that all follows from the Wigner-Eckhart theorem. Now then, allow me to find a new pad of paper, because I want to keep this one as it is. And what I'd now like to do is to address an interesting issue, which is that, in fact, maybe if I can go back for a minute, is that all of these moments which appear, these are moments appear classically for a general charge and current distribution in classical E&M, you would have an infinite series of these moments here. There would be an infinite number of them. I've just given the leading terms here. However, in quantum mechanics, it turns out that only certain select numbers of these, or numbers of these moments appear. There are some that are forbidden, and I want to tell you now about which ones are allowed and which ones are forbidden. There are basically two rules which govern which multipole moments are allowed in a nucleus. So the rule one is this. The rule one says that odd electric poles and even magnetic poles and even magnetic poles are forbidden. And the reason for that is something I will explain by means of an example. Let's take a look at the E k equals 1 electric odd pole. This is the electric dipole moment. And the statement is that the electric dipole contribution to the expansion of the potential does not occur. Why is that? Well, let's look at what would happen if it were there. The potential for the electron moving in the field of the nucleus is, of course, the charge of the electron, which is minus e times the scalar potential phi. And if you look at this, this contains in the dipole term, it'd be minus e, the dipole moment dotted into x divided by r cubed. That's the second term in the expansion here. Of course, the monopole term right there, that's the term that gives you the Coulomb field of the nucleus, and that's what that's the largest term, and that gives you the electric field which the electrons orbiting the nucleus move in, and so the overall structure, the main structure of the atom is determined by just the monopole term. But let's move on and look at the dipole term, which is the next term. If that one is present, then we get a contribution to the potential of the electric field which the electron is moving in, which is given by this quantity I put in square brackets. The dipole moment vector, on the other hand, has to be proportional to the angular momentum of the nucleus, because on a single irreducible subspace, all vector operators are proportional. And so if I call this H1, let's say H1 referring to the perturbation on the atomic Hamiltonian, which is responsible for the electric dipole moment of the nucleus, then it has the form of minus E times K times the nuclear angular momentum I dotted into the position vector X divided by R cubed. Now, the question then is, what horrible things will happen to our atomic Hamiltonian if such a term is present? Why is it bad? Well, let's look at what happens to this Hamiltonian under parity. Let's take H1 and conjugate it by parity. Under parity, all spins are invariant. All angular momenta are invariant under parity. It's one of the basic properties of parity. Whereas the position vector X flips sign. And so you see under parity, H1 gets mapped into minus H1. And therefore, if such a term is present in the Hamiltonian, it means that the system does not conserve parity. What about time reversal? Let's take theta and conjugate it with H1. Nice antilinear operator. Under time reversal, all angular momentum do change sign, but the position vector does not. And so once again, this goes into minus itself. And the result we see is that if there's such a term, if the electric dipole term are present in the atomic Hamiltonian, it would mean we would have a contribution to the Hamiltonian which violated both time reversal and parity. Now, in fact, we know that time reversal and parity are violated, both of them by the weak interactions, and both of them at quite a small level. But this is known to be a fact that's determined experimentally. And so the question arises then is, why don't these terms then appear maybe at some small level inside atoms? Or another question to ask is, has anyone ever gone and done the experiments to look for these terms inside atoms? And the answer is yes, they certainly have. And the current experimental situation is that in spite of really rather intensive efforts to measure very small effects, no one has ever detected a non-zero electric dipole moment of a nucleus, or for that matter, of other particles such as the proton, of course, could be a nucleus, or the neutron, or the electron itself. In fact, Gene Cummins, who is a longstanding and most excellent physicist, experimentalist in our department, spent years of his career working on trying to detect an electric dipole moment for the electron. And he succeeded in lowering the upper bounds that are known experimentally, but he never got an actual value for one. So the current experimental situation is that if such moments exist, they are below what can be currently detected experimentally. It doesn't mean they don't exist. What about theory? Does theory explain why they don't exist, or what's the status of that? Well, in the theory of quantum chromodynamics, it turns out, we know that there are both a parity and CP violating effects in QCD. This is well known. It turns out that in the case of a particle like the neutron, that current theories of QCD indicate that the neutron ought to have a non-zero electric dipole moment at a level which is above the current upper limit, which is determined experimentally. And so what that means is that there's basically a disagreement between standard QCD and experiment. And this is obviously an opportunity to look for new physics. So the question then is, can this lack of an electric dipole moment be explained by theorists? Well, the short answer to that is that theorists can explain anything if you give them enough time. And so one of the possible explanations they've come up with as to why we don't see such an electric dipole moment has to do with the existence of a hypothetical particle called an axion. If the axion exists, it suppresses the CP violation. This is called the strong CP problem, by the way, in the business. The existence of the axion would explain why we don't see it at the level we do, or the level we don't, I should say. The axion has also become a candidate in recent years for dark matter. The amount of dark matter in the universe is much larger than the amount of visible matter. So if axions exist, there's plenty of them around. But in spite of intensive searches, nobody's ever been able to detect an axion either. If someone does finally, and it turns out the axion is the explanation for the strong CP problem, it'll be nice physics beyond the standard model, and it'll also be of astrophysical importance as well. Anyway, that remains to be seen. As time goes on and the experiments continue to be more and more negative, people are getting discouraged. Anyway, that's the current situation on this. In any case, that's the background on this rule here of the excluded or the forbidden or so-called forbidden electric and magnetic multiple moments. Now, the second rule says that the K value of the moment, which is the irreducible is the rank of the irreducible tensor operator corresponding to the moment, that this has to be less than or equal to 2I, where I is the spin of the nucleus. So what does that mean? Let me just give you some examples first. For example, if we talk about the proton has a spin I equals to 1/2. That means that the K value can either equal to 0 or 1, but it can't be any higher than that. If we go back to our series here, this means that in the case of the proton, it can have the electric monopole moment, that's K equals 0. In fact, we know that it does, that's just the charge in the electron. And it could also have a magnetic dipole moment, that's a K equals 1. And indeed, we know that a proton does have a magnetic dipole moment, that's true. But the electric dipole moment's excluded, but because of time reversals I just explained, and the quadrupole moment's excluded by this rule. It says that K has to be less than or equal to 2I. So a proton has only these two moments according to these rules that I explained. On the other hand, if you take a deuteron has spin 1, I equals 1. That means K could have the value of either 0, 1, or 2. So a deuteron could have a charge, which it does. It could have a dipole moment, a magnetic dipole moment, which it does. Experimentally, this is known. And it could potentially have an electric quadrupole moment. Now the question then arises, does it have an electric quadrupole moment? The answer is yes, the deuteron does. It was discovered experimentally by Isidore Rabi in 1939 at Columbia University, and it caused quite a stir at the time because it indicates something about the wave function of the proton and the neutron as they orbit each other inside the deuteron. In particular, it tells us that the wave function, the radial wave function for this nice two-body problem is not purely an S wave, even though it's a ground state, but rather it has some admixture of a D wave as well. And from the known measured quadrupole moment, one can get information about the D wave component of the wave function of the deuteron. All right, anyway, so the basic rule seems to be that if the moment is allowed by these rules, that it actually occurs. By the way, if you had an alpha particle, let's do another example. If you have an alpha particle which has spin 0, that's of course the nucleus of helium, then the rule says that K is only equal to 0. K max is equal to 0. So the alpha particle can have an electric monopole moment, that's a charge, which of course it does have that, but it can't have anything else. It does not have a magnetic dipole moment or nor electric quadrupole, nor none of the others. Those are out completely. All right, so those are the two rules. All right. Now, what I propose to do in the rest of this lecture, going back to my general series here, is let's study the effect of the hyperfine effects on a model system that we can analyze. We're basically going to be working with hydrogen, slightly more general than that actually, and we're going to allow for the electric monopole, which of course we have to, and the magnetic dipole, and we'll ignore the electric quadrupole term. If we were talking about ordinary hydrogen, there is no electric quadrupole term. If we are talking about deuterium, where the deuteron is a nucleus, then this term would be there. However, it turns out it vanishes in the ground state because of selection rules. So actually the calculation we do will apply to a deuteron as well. But anyway, the main point is we're going to concentrate on the most important of the hyperfine corrections, which is the one which comes from the magnetic dipole moment. So basically this then is our vector potential for the perturbation, which we want to consider the perturbation on the orbital motion of the electron around the atom. This mu that appears here, by the way, is the magnetic moment of the nucleus, and so we'll need to be more careful about that in a minute, because the electron also has a magnetic moment. It's not the same. All right. Now that means we want to talk about a Hamiltonian for our atom, which looks like this. It's going to be 1 over 2m. We have p minus, it's really p plus e over ca squared, because the charge is negative, squared, plus the potential energy v of r. And then we have minus the electron magnetic moment mu e dotted into the magnetic field. And to this, I'll add the fine structure terms, and I'll add some terms that are responsible for the Lamb shift. We don't need to know much about the Lamb shift, but I'll put it in anyway. The reason being that the hyperfine effects that we're studying are numerically smaller than the Lamb shift. And so we want to do a realistic treatment. That's my aim tonight, is to do a realistic treatment of the hyperfine effects, at least in hydrogen. And so you have to include the Lamb shift here. Also, the Lamb shift causes a splitting of the fine structure levels, as you'll recall, depending on the L quantum number. And knowing what the degeneracies are of the eigenstates of the unperturbed Hamiltonian is, of course, important in perturbation theory. And so for that reason, the Lamb shift is also important. Now, this is the total Hamiltonian we'll use. This could be the Hamiltonian for the Zeeman effect in an external field if A and B were external A and B. But for this problem, they aren't, they're internal. And the A is given by mu, it's really the nuclear mu crossed with x divided by r cubed, as we have seen. That's the magnetic dipole contribution to the vector potential. So that's the A that's going to go in there, and the B that goes into there is equal to del cross A. It's the curl of this A. So this defines the Hamiltonian that we're going to use. By the way, the nuclear magnetic moment here, not to be confused with the electric magnetic moment, the nuclear magnetic moment, as I've mentioned already, is proportional to the nuclear spin. And the nuclear spin acts on the nuclear Hilbert space. So the Hilbert space for this Hamiltonian that I've written down is, let's call it the Hilbert space for the electronic part. This is what we would have in the, just for the fine structure model that we talked about in the last lecture, tensor product with the nuclear, the Hilbert space for the nuclear part, which I described a few minutes ago. It's a standard nuclear Hilbert space. So compared to the fine structure model, we have an enlarged Hilbert space. We have new operators which act on the nuclear Hilbert space. And this is going to give rise to new quantum numbers and splitting and so on, as we'll see as we proceed through this. Now then, the most immediate problem, by the way, are there any questions at this point before I make a fairly serious digression? All right then. The digression that I want to make concerns the fact that this vector potential, which appears in this Hamiltonian that we want to analyze, is rather singular, as you can see, as r goes to 0. It behaves rather badly. The vector potential diverges as 1 over r squared, and it has an angular dependence, which is non-trivial. If you take the curl of it to get the magnetic field that appears there, then this has a worse divergence. It goes as 1 over r cubed at the origin. And if you do this naively, what you're going to find out is you get in perturbation theory, is you get matrix elements that are actually not defined because of the singularity. They either diverge or they're 0, and you can't tell which, or something in between. So we're going to fix this up. The problem here is that this vector potential that I've written down is the vector potential for a point dipole. If this were valid all the way down to r equals 0, then it represents an idealization in which there's a current which is singular at the origin. If I go back to my original classical picture here, this dipole moment, this was talking about a field point that's outside the charge distribution, So that's so this formula here, you don't take the field point all the way down to r equals 0. But if I just use the formula itself, as if it were valid all the way down to r equals 0, then I got a problem. All right. So what we need to do is to smooth out this singularity at r equals 0, and we're going to do this by using a device which is a standard calculation in courses on E&M. You can read about it in Griffith's books, for example. The device is the following: is we're going to replace the point dipole at the origin by a uniformly magnetized sphere. And we want to make the total magnetic moment of the sphere equal to the known magnetic moment of the nucleus. Let's say that the mu is given here and is fixed. The sphere is uniformly magnetized, and magnetization M is defined as the magnetic moment per unit volume. And so what we want the magnetization of our sphere to be equal to the net magnetic moment mu divided by the volume of the sphere, which will be 4/3 pi a cubed, where a is the radius of the sphere. And that means that inside the sphere, the magnetization is uniform and, let's say, points in the vertical direction. Now, if you remember how the story goes from Griffith's book, if you used his book, when you solve for the fields, you find that the magnetic field inside the uniformly magnetized sphere is in the same direction as the magnetization, and it is, moreover, uniform itself inside the sphere. But outside, it creates a dipole field, and so you get this kind of a picture for the magnetic field. These are magnetic field lines that I'm drawing here now. And then there's a central line like this that goes up and down like this. So these are the B lines, like so. It's uniform inside and dipole outside. That's the conclusion. So what I'm going to do is to remind you of this construction out of Griffiths or Jackson or other books, and then in the context of this problem that we want to solve. So we're going to create a sphere that has some, and by the way, the strategy we'll follow is to work out the vector potential and magnetic field for the uniformly magnetized sphere of a radius A. And then in principle, at least, we'll use those fields in the perturbation calculation. Then we won't have any singularities or any infinities, and all the integrals will be well defined. Then after the integrals are taken, then we let A go to 0, and we'll find we get results that are physically meaningful and effectively converts this sphere into a point dipole. That's the strategy to use. If you try to just do it with a point dipole alone, you get confused. It's hard to understand what's going on, and you get things that are really not defined. And by the way, this is also physically reasonable because the nucleus is not a point charge anyway. All right, anyway, so let me put axes here, X, Y, and Z here like this. And let me draw a sphere here, which is supposed to be the sphere of uniform magnetization. And let me put a field point X out here at which we wish to measure the vector potential like so out there at this point X. Now, we have some magnetization inside this. Let me draw a little volume element here like this and call it d cubed X prime. X prime I'll use as a variable of integration that runs over the source distribution, whereas X is the field point at which we evaluate A of X. That's what we're interested in. By the way, I've drawn this as if this is an external point, but we might want it to be an internal point as well. In any case, it's some field point. This d cubed x, x prime, this volume element, which is at location x prime, let's say, like so, x prime, has a magnetic moment, which is the magnetization, magnetic moment per unit volume, multiplied times d cubed x prime. And this gives a contribution to the vector potential at the field point, which is really just a given by a version of our formula. Let's see right here, a version of this formula here, except for the mu, what we want to replace it by is the magnetization from the little element, which is that thing right there. And instead of the x, we want to replace it by the x minus x prime. So we take this and we cross it into x minus x prime, that vector, and then divide by x minus x prime cubed, like that. And that's the contribution to A from this little volume element. We then now integrate this over the volume, so the d cubed x prime runs over all the volume, and this then gives us the vector potential at the field point. That's the idea. Now for our problem, it simplifies because we're assuming the magnetization is uniform, so I can take this m out, and this becomes equal to the magnetization, constant magnetization m, crossed into an integral over the volume v, d cubed x prime, times the x minus x prime divided by the thing cubed, like that, the distance cubed. And so it's a constant magnetization times a certain integral. The magnetization, on the other hand, is the desired magnetic moment mu divided by the volume, 4/3 pi a cubed, because it's total magnetic moment divided by the total volume. That's what m is. By the way, when we let the charge, when we let the radius of our sphere go to 0, you can see that the magnetization inside the sphere goes to infinity because mu is held fixed. So it's a singular limit, you see. All right, in any case, this is the m that we have here. And then this is then crossed into this integral. Now this integral is actually pretty easy to evaluate, because if you look at it, you can see that it has an interpretation in electrostatics. By Coulomb's law, this integral is equal to the electric field that we would see at the field point. Let me write it as E of x, due to a charge distribution inside the sphere, which has a charge density of 1. That's because there's no rho under this integral. So let's think of a charge distribution, rho of x prime. The prime means, inside the distribution. And that's equal to 1 if r prime is less than a, and it's equal to 0 if r prime is greater than a. It's just a uniformly charged sphere, that's all. Well, this is get crossed into E of x. But if that's what this integral is, it's that E of x. However, that E of x can also be evaluated by using Gauss's law because it's a spherically symmetric distribution, and so it's a radial electric field. And so by Gauss's law, E of x is equal to x vector divided by r cubed, multiplied times the charge q of r, where q of r is equal to the charge inside radius r, And do we have room to write this out? This is equal to, what is equal to the charge inside radius r? It's equal to 4 pi over 3 r cubed if r is less than a, and it's equal to 4 pi over 3 a cubed if r is greater than a, because outside you just get the whole charge inside the sphere, and there's nothing new as r increases. All right, so that's the q of r. So I can plug that into there, and I can put E of x into there, this Gauss's law calculation. And the 4 pi's and so on are going to cancel out. And if you do, here's what you get. And this is certainly a formula you can find in the E&M books, is you'll find that we get it here. You'll find that the vector potential A at field point x is equal to mu crossed into x multiplied times 1 over a cubed if r is less than a, and 1 over r cubed if r is greater than a, like so. And you may notice, by the way, that in the exterior region, you get mu cross x over r cubed, which is the same as the vector potential of a point dipole. So in the exterior region, you can't tell the difference between a point dipole in this uniformly magnetized sphere as long as the total magnetic moment is the same. This, of course, is the same situation that happens in electrostatics or in gravitational problems, in which if you have a spherically symmetric charge or mass distribution, then the electric or gravitational field is the same as it would be if all the mass or charge were concentrated at the origin. This is something that was originally proved by Newton in connection with gravity. So I'm sure you're quite familiar with that fact from physics 5 or 7 or high school physics. And this is a magnetic analog of that. But this formula also gives you the vector potential inside the sphere as well, and the denominator is a constant now. If we take the curl of this, and I'll spare you the algebraic details of doing the curl, what this turns into is there's an interior region, an interior result, which is twice mu divided by a cubed. This is the region where r is less than a. And outside, it's given by mu dotted into a certain tensor I'll call t divided by r to the fifth. And this is where r is greater than a. And this tensor t is the same one I've introduced earlier, and I'll just copy it down again. It's 3xi xj minus r squared delta ij. This is a tensor that occurs in the electric quadrupole moment, the electric quadrupole term, but as we see, it also occurs in the magnetic field of the magnetic dipole term, same tensor. When I say mu dotted into the tensor and I draw a double arrow over it to indicate it's a tensor, the double arrow really means it's something like a matrix, and you can think of this as matrix multiplication if you want. So this is just the vector mu dot multiplied on the left onto this matrix. If I want to write this out in components, what this thing means is that the ith component of the magnetic field is equal to the sum on j of mu sub j times tji divided by r to the fifth. I think that's makes it clear what the notation means. Anyway, just doing the curl, this is what you get. And you see that the magnetic field inside, the interior solution for the magnetic field is in fact uniform and constant. And that's the same as this picture that I drew here on the inside. But the outside, it's actually a magnetic dipole field, and that's what this is with the magnetic moment mu. All right. So that's the A and the B then. All right. Now it helps to streamline the notation a little bit here. Allow me, I can put these cases into a single formula if I make some definitions. Let's make some definitions here. Let's define a function I'll call delta of r, which is equal to 1 over a cubed if r is less than a, and it's equal to 0 if r is greater than a. And I'll define a function I'll call f of r, which is equal to 0 if r is less than a, and 1 if r is greater than a. And if I do that, then I can take these two formulas and put them together in a better way. I can write a of x, then the vector potential is equal to mu cross x multiplied onto delta of r for the first term, that's the 1 over a cubed, plus f of r divided by r cubed. And likewise for the magnetic field, b of x can be written this way, is that it's mu dotted into, I can write it as twice delta of r times the identity tensor. That's the first term here where I get 2 mu over a cubed, you see. And then for the second term where I've got the t thing, this can be written as f of r over r to the fifth times the tensor t, like so. And this is a more abbreviated way of writing the magnetic field and the vector potential in single formulas, including both the interior and the exterior regions. Now, as I mentioned, we're going to be interested in taking the limit as a goes to 0. Properly, we should only do this after we do matrix elements. In any case, if we take a equals to 0, then this function delta of r, look what happens is, as a goes to 0, the region over which this is non-zero shrinks smaller and smaller, but the value of the function gets bigger and bigger because it's 1 over a cubed. On the other hand, the integral of this function over all space is constant. It's just 4 pi over 3 because the volume is 4 pi over 3 times a cubed. So as a goes to 0, the function delta of r approaches a delta function that's 4 pi over 3 times the three-dimensional delta function delta cubed of x. That's the limit of that. Whereas the limit of f of r as a goes to 0 is f of r is just 1 everywhere except for a small region. The region shrinks as a goes to 0. So f of r just goes to 1 in the limit. So these are the limits that we want to take. If you look up books on hyperfine effects, what they'll do is they'll take these limits on these formulas here. And if they do, the capital delta then gets replaced by Dirac delta functions at the origin. When this happens, these terms that appear there are called Fermi contact terms. Fermi gets his name on it because he carried out this calculation originally. He and Segre did. Segre, by the way, is one of our faculty members too, some years ago. We never had Fermi, but we had Segre. In any case, Fermi-Segre contact terms, because they're called contact terms because of the delta function that appears there in this limit that a goes to 0. What that delta function means is that these terms don't contribute to the energy of the Hamiltonian or to energy of the quantum system unless the electron and the nucleus are sitting on top of one another. And that's why it's called contact terms. By the way, that also means that these terms only contribute for S waves, L equals 0, because as we've seen, only S waves have a non-zero value at the origin. When these are replaced by true delta functions, the integrals will all be 0 for any wave, any angular momentum value L, except for L equals 0. So the Fermi contact terms only apply when L equals 0. It turns out the other terms only apply when L is not equal to 0. We'll see that too. All right, in any case, this is the setup of the A and the B. Now, this was just merely all we've done in this rather large digression is to smooth things out. But what we need to do now is to go back and put it into the Hamiltonian. So let's talk about that. Let's see, somewhere back here I had the Hamiltonian. Yes, here it is. Here's the Hamiltonian. Here's the full Hamiltonian like this. So the A and the B which appear here are and the B which appears there. This is the A and the B that we just worked out, which for a finite smearing of the nucleus is going to be given by these two formulas here. However, the mu that appears in this A and B is actually the nuclear mu. So let me put that in. Whereas the mu that appears here is the electron mu. That's electron magnetic moment. All right. Now, we'll handle this Hamiltonian pretty much like we did the Zeeman effect. We'll expand out the kinetic energy and you get two terms. You get a cross term, you get an A squared term. The A squared term is really utterly negligible because the cross term is already quite small. And if I do this, then let me put it on another page over here. Let me put it down here. Then what we get is what I'll call an unperturbed Hamiltonian, which is p squared over 2. In fact, I'll switch over to atomic units now, which is helpful. So I don't need to worry about the mass. It's p squared over 2. Oh, well, maybe I won't do that yet. It's p squared over 2m. I'll leave it in for a minute. And then we have plus the potential V of R. And then we have the fine structure, H fine structure. And then we've got the hyperfine structure, the Lamb shift. This H0 is the Hamiltonian that we discussed in the last lecture and the previous lecture on fine structure. So you know what its energy levels and degeneracies look like. The H1 is the terms that come from the interaction with the nucleus, and they're going to be an E over MC times P dotted into A. That comes from the cross term in the kinetic energy minus the electron mu E dotted into the magnetic field. And there's an H2 which goes like A squared, and goes like A squared, and we're going to neglect that because it's really small. So this is the Hamiltonian we're going to use. This H1, if you like, is H hyperfine structure, H sub HFS, if you want. It's the same thing. This is describes a hyperfine structure. But remember that the A and the B that occur here are determined by the nucleus, so they actually involve the nuclear angular momentum appears inside A and B. So these are really operators that act on the nuclear Hilbert space. All right. Now, so let's put the pieces together then. So these two terms here, the first one, let's call it the orbital term, and the second one, let's call it the spin term. Let's work on them one at a time. So H1 orbital is going to be E over MC times P dotted into A, but the P is dotted into the vector potential A is mu cross, this is mu nuclear cross X. This is multiplied times delta of R divided by A cubed plus F of R divided by, excuse me, it's just delta of R. Get it right, it's delta of R. Now, delta of R is 1 over A cubed plus F over R times 1 over R cubed. That was the expression for the vector potential A. As far as this factor here is concerned, let's work on this. We can rearrange the triple product doing the mu n first. The mu n is the G factor, the nuclear magneton, and then the nuclear spin I divided by H bar. That's the mu part. That gets dotted into X cross P, which is the orbital angular momentum. All right. And so we get a term that goes like I dotted into L, the nuclear spin dotted into the orbital angular momentum here. The EH bar, the E over MC, let me multiply and divide by H bar. And let me multiply and divide by 2, because if I do, then I get a Bohr magneton here. And at this point, I'm going to start letting H bar equals to 1, because that saves writing. Or you can go to atomic units if you want. But anyway, that means the H1 orbital looks like this. There's a factor of 2 there. There's the Bohr magneton, mu B. There's a nuclear G factor, Gn. There's a nuclear magneton here from that. The H bars I'm dropping. What's left over is simply I dotted into L, like this, multiplied onto delta of R plus F of R over R cubed. I think I'm making a mistake here. No, this is actually all right. This is actually all right. All right, so that's H1 orbital. All right, we box that. Let's also work on H1 spin. So this is minus mu B, the electron magnetic moment dotted into the magnetic field B. This is the B determined by the nucleus. And that, to remind you, is here. It's this nuclear magnetic moment dotted into this tensor thing here. So I need to dot that with mu E. So let's put the mu E on the right-hand side. Anyway, minus mu E, the electron magnetic moment, is equal to, with a plus sign, it's the electron G factor times the Bohr magneton times the electron spin over H bar. And I'm going to replace electron G factor by 2 because this is already a pretty small correction. So if we do this, then H1 orbital is equal to, it's H1 orbital is equal to the so we got the minus mu E, that gives us a 2 times the G electron times mu B times the spin S. And I'll drop the H bar because I'm setting it equal to 1. Dotted into the magnetic field. The magnetic field is here. I see I should have put the spin on the right-hand side because I've got the nuclear magnetic moment on the other side. So let me do that right. Let's do it like this. H1 orbital is going to be, as far as the B part here is, it's a nuclear magnetic moment. So this is equal to the nuclear G factor Gn m sub n times I, and I'll ignore the H bar. This is then multiplied onto this tensor, and then on the right-hand side, we've got we've got this minus mu E, which is a Ge mu B. Ge is replaced by 2 times the spin S. So this becomes equal to twice G nuclear Bohr magneton, nuclear magneton, multiplied times I, sandwiched around this tensor, which is twice delta of R times the identity tensor, plus F of R over R to the 5th times this tensor T. And on the other side, we've got the electron spin S, like so. All right. And so this is H1 orbital. All right. So here's the perturbation. Now,
Professor,
yes, question.
that should be H1 spin.
Thank you. It should indeed be H1 spin. So we've got orbital plus spin. You see the way I've set it up, we've got a common factor here, which I get tired of writing. So let me write K here is equal to 2 times really the 2 is the G factor of the electron. So it's the product of the two G factors times the product of the two magnetons, the Bohr and the nuclear magneton. Let's write that K here. And so that'll simplify the writing. All right. Now then, I think this is what I want. All right, now, let's see. Let's talk a little bit about how we're going to use this in perturbation theory. To go back to the Hamiltonian, here, as I said, is the unperturbed Hamiltonian right there. It's just what we studied when we were doing fine structure with some comments about the Lamb shift. So we know what the energy eigenstates are. They have quantum numbers N, L, J, and MJ. I hope you know what those mean. However, because the Hilbert space has been multiplied also by the nuclear Hilbert space, to get the complete set of basis states, we need to multiply by IMI to represent the state of the nucleus. So these are the eigenstates then of this unperturbed Hamiltonian. The energy levels have the form of E, N, L, J. If we just did fine structure, it would not have an L dependence, but that comes because of the Lamb shift. In fact, the main reason I put it, one of the reasons I put it in is because it gives us an L dependence on the energy levels. So the energies do not depend on the MJ or on the MI quantum numbers. And therefore, these states have a degeneracy, which is 2J plus 1 multiplied times 2I plus 1. See, if we didn't use the Lamb shift to split the L degeneracy, then the degeneracy would be larger than that because we'd have degeneracy between different L values. So this simplifies things, but it's also realistic too because the Lamb shift is larger than the hyperfine structure. In any case, this means we have to deal with think about anyway, degenerate perturbation theory because the eigenstates of H0 are degenerate. This could actually be a rather large number here. So again, we have to worry about, do we have to diagonalize large matrices? All right. Now, so let's address that question then. So that means that we're going to be dealing with matrix elements that look like this. We'll have NLJ. Oh, I'll tell you what, before I continue, this product of the fine structure states for the electron multiplied by the usual basis states for the nucleus. This is a product of two standard angular minimum bases. One is a JMJ and then is an IMI. So I'm going to call that the partially coupled basis. Let's talk about this here. The partially coupled basis. The partially coupled basis is equal to NLJMJ times IMI. And I'll abbreviate that as NLJ MJ M sub I. Or I can even put the I in here if you want. The I is a constant, but I can put it in MI like so. And the energy levels are determined by the NL and J quantum numbers. And the MJ and MI quantum numbers are the labels of the basis vectors inside the degenerate eigenspace. I call it partially coupled because in order to get J, we had to already couple together orbital and spin angular momentum. But we have not yet coupled that with the nuclear angular momentum. That's why it's only partially coupled. However, we can also create a fully coupled basis, which is obtained by combining J plus I. J is, of course, the entire angular momentum of the electronic part of the Hamiltonian. We add to that the angular momentum of the nucleus to give us the total angular momentum of the entire atom. This is the same thing as L plus S plus I. It's a sum of 3 angular momenta. And it's standard to call it in this business F. F is the usual symbol for the total angular momentum of the atom, including the nucleus. And so the fully coupled basis then, I need to get a paper for it. The fully coupled basis then is going to be, it'll look like this. It'll be N, L, J, F, and M sub F. And it's equal to a sum on the magnetic quantum numbers MI and M and MS. Excuse me, MI and MJ, MI and MJ. of NLJ M sub J M sub I times the Clebsch-Gordon coefficient that you'd get by combining J with I. So it's JI, MJ, MI, giving you a total value of F and MF, like so. And as I say, we'll call this the fully coupled basis. All right. Now, both these bases appear here on this page. And if I pull it further back down, so does the Hamiltonian here. Both this Hamiltonian is these two expressions here for the orbital and spin contributions to it. The energy eigenstates are characterized by an L quantum number, as we know. But as I mentioned earlier, the contact terms, which are the first terms here involving this capital delta function, vanish unless L is equal to 0. So to simplify the calculation, let's start with, we can take two cases, one where L is non-zero and one where L is equal to 0. Let's start with L non-zero. If we take L not equal to 0, then we can just drop the contact terms entirely, and we only need to deal with these latter terms, the one that have the function f in them. Moreover, the function f goes over into just 1 when we take the limit as a goes to 0. Like that, it just becomes 1. So what that means is we end up with, let me see if I can do it here, we end up with an effective Hamiltonian. So for L not equals to 0, we end up with a H1 effective, which has both an orbital and a spin contribution. And we can write it this way as K for the leading factor here, times the nuclear spin I, which is dotted into, here's the 1 over r cubed. It would be dotted into, it's dotted into L divided by r cubed. You see it's I dot L here, so it's I dotted in L, the L over r cubed, we drop the F because it approaches 1. So that takes care of the orbital part. For the spin part, we get a plus this, let's see here. I'm sorry, let me do it this way. Let me do it right. Let's do H1 effective. We'll write it as K. Then we'll have I dotted into, let me write it this way, I on this side. Excuse me a second, I'm confusing myself. Yeah, all right. Yes, this is okay. It's going to be I was doing it right the first time. It's L divided by r cubed. This gives me the I dot L divided by r cubed up here. And then for the second term, what I want to do is to add this. I want to take the F I'll replace by 1. I want 1 over r to the 5th times the tensor T multiplied onto S. And that gives me 3x times x dotted into S minus r squared times S squared. And it gets divided by r to the 5th. All right. And that takes care of the spin part of the effective Hamiltonian. Let me box that off because this is a Hamiltonian we're going to use for our perturbation calculation. So this is H1 effective. Allow me to take this quantity in the square brackets and give it an abbreviation. Let's just call it the vector G, just to give it a name. The vector G depends on the dynamical variables involving the electron. Here's its spin, here's its orbital angular momentum, here's its position, x in the magnitude position, and so on. But it does not involve the nuclear angular momentum. That's this factor here. So this takes H1 effective, and it's a dot product then between the nuclear angular momentum and an electronic vector operator. G is a somewhat complicated electronic vector operator. All right then. So to think about the
I have
perturbation.
a question.
Yes.
Why is it s squared and not just s vector and the minus r squared s squared in your definition of G?
It shouldn't be s squared. It should be s vector. Thank you. It should be s vector. Thank you for catching that. All right. So now, then the perturbation calculation, we're going to need to think about matrix elements that look like this. Is NLJ FMF. I'll use the fully coupled basis. and then we have a constant k out front, and then we have I dotted into G, and then we've got N, L, J, F, and MF on the right-hand side. Now the NLJ identifies the unperturbed eigenspace, and the F and MF identify the basis vectors inside that degenerate eigenspace. So in principle, we ought to put primes on the F and MF on one side of this matrix element to create the matrix that we need to diagonalize for first order degenerate perturbation theory. However, F being the total angular momentum of the system, which is J plus I, generates rotations in both orbital and spin degrees of freedom. Both orbital and nuclear spin degrees, both electronic and nuclear spin degrees of freedom. And so the rotations generated by F rotate both sides of this dot product, and therefore this product commutes with all three components of F. It's a scalar, in other words, under the total angular momentum of the system. Obviously, we'd expect it to be a scalar because these hyperfine effects are determined internally and they don't depend on the orientation of the atom. But in any case, in detail, this is how it works out. And what that means is that this operator I dot G commutes with all three components of F. It therefore commutes with F sub Z and also with F squared. And so for that reason, this matrix element is diagonal in the quantum numbers F and MF, and I can remove the primes there. If I had used the only partially coupled basis, I would have had MI and MJ corresponding to operators IZ and JZ, and this perturbing Hamiltonian does not commute with them. So I would have a full matrix then and have to do some diagonalization. So by using this fully coupled basis, you see we have escaped from having to diagonalize matrices in degenerate perturbation theory. Yet again, we'll see how many times this happens in this course that we get to do that. All right. Now the problem then is to evaluate this matrix element to get the energy shift. So the energy shifts are going to be the diagonal matrix elements of this thing. And now the problem is to evaluate them. The first step that we use is we notice that the J values are the same on both sides of this matrix element. And we therefore invoke the projection theorem, which I explained and I outlined the proof of in the last lecture, which allows us to replace G by the following: J, angular momentum J times J dotted into G divided by JJ plus 1. And if we do this, then I dot G goes into I dot J times J dot G divided by this. All right. Now let's analyze this a little bit. Let's look at J dot G. What is that? Let's do a calculation here. Let me draw below this line. J dot G is equal to L plus S, but because that's what J is, dotted into G, which I'll copy from above. It's L vector over R cubed plus this, what's left of this tensor, 3x times x dotted into spin S minus R squared times spin S divided by R to the fifth. And let's just do the algebra and multiply this out. So first I'll dot the whole thing with L. The first term gives you obviously L squared over R cubed. As far as the second term goes, L dotted into X is 0. That's because L is X cross P. So by the triple product, it just gives you 0. So that term doesn't contribute. As far as the second term is concerned, I get an L dot S with a minus sign. R squared over R to the fifth is R cubed. So I change that to a minus sign. I get an L squared over R cubed, right? So it cancels out this first term that we saw. Now then, let's do the S. We get an S dot L, or an L dot S, if you will, divided by R cubed. And then for the, excuse me, I did this wrong. So multiplying through by L, the first term gives me L squared over R cubed. That's correct. That's that term here. Now I want to take L and dot it into this term. As I said, the first term goes away because L dot X is 0, because L is X cross P. As far as the second term, I get L dot S divided by R cubed with a minus sign, minus L dot S divided by R cubed. Now let me multiply through by S. The first term gives me a plus L dot S divided by R cubed. And as far as the last term is concerned, when I multiply that out, it gives me 0. I'll show you why that's so. It's because basically I get 3 x dotted into S quantity squared minus R squared times S squared. But x dotted into S squared is the same thing as 1/4 xi xj sigma I sigma j. And if you use the rules for the Pauli matrices, that just turns into 1/4 R squared. So overall, the first term is 3/4 R squared. But the operator S squared is 3/4, so you subtract 3/4 R squared and it just gives you a 0. These two terms cancel also, and you have the nice simple result that this j dot g is just equal to L over R cubed. So that's this factor that's going to go in there. So if we put that together then, make some space here, and make sure I'm on screen, then we get the delta E is equal to the K times the matrix elements here, NLJ, FMF on one side. And then in the middle, what we have is we have I dotted into J, and then the J dotted into G turned into L squared over R cubed. And there's divided by JJ plus 1 that came from the projection theorem. And then we've got the NLJ, NLJ FMF on the other side, like that. All right. Now, the L squared obviously is acting on an eigenstate of itself, so it just turns into LL plus 1, which is a C number and can be taken out of the matrix element. The JJ plus 1 I can also take out, obviously. As far as I dot J is concerned, we use the fact that F is equal to I plus J. And if you square both sides, you get I dot J, and solve for the cross terms, you get I dot J is 1/2 of F squared minus I squared minus J squared. So this I dot J is a sum of 3 operators which are acting on eigenstates of themselves. It's an eigenstate of F squared, J squared, and I squared. The I was suppressed, but it's an eigenstate of I squared as well. So this turns into a C number, which is 1/2 of F times F plus 1 minus I times I plus 1 minus a J times J plus 1. And then the only thing that's left in the middle is the expectation value is 1 over R cubed, and you end up with the expectation value of 1 over R cubed, which we saw before in fine structure. It's 1 over A naught cubed, 1 over N cubed, 1 over L times L plus 1/2 times L plus 1. And we're glad we did that exercise on expectation value. This is for hydrogen now. That homework problem on those expectation values. This applies only for L not equals to 0, but that's the case that we're looking at right now. So we're able to evaluate this matrix element by using all the tricks in the book. And when we do, we end up with a formula for the energy shift, and here it is that delta E is equal to twice the nuclear magneton, the nuclear G factor, G sub n, times the product of the Bohr magneton times the nuclear magneton, divided by A naught cubed, put it like that. And then we get F times F plus 1 minus J times J plus 1 minus I times I plus 1 in the numerator. And in the denominator, we get a J times J plus 1 times a 2L plus 1. There was an LL plus 1 upstairs. It canceled out the 2 factors of the expectation value of 1 over R cubed, and the L plus 1/2 got multiplied by 2 that turned it into a 2L plus 1. Anyway, this is the formula we got. And that's kind of the grand result for this whole hyperfine structure calculation. So we need to understand it and make some interpretation of it, which I think we have time to do. Before I go on, are there any questions about this derivation? It's a fair amount of algebra to do it, as you can see.
I had a quick question about the projection theorem when we used it here.
Yes.
So we use J because the G operator is defined on the electronic Hilbert space, right? That's why we didn't use F.
That's right.
Okay, thank you.
We actually have three angular momenta floating around here, if not more. We've got L, J, and F, and they're the same on both sides of the matrix element. So you could use the projection theorem in three different ways, but this is the one that works for this problem. It gives you the best avenue for getting the answer. All right. So this calculation was carried out in units in which h bar was equal to 1, but if you go back to ordinary Gaussian units, the product of two magnetic moments divided by a distance cubed has dimensions of energy, and everything else here is dimensionless. So this answer is actually correct in Gaussian units also. If you wanted to put it in SI units, you'd have to worry about a notational conflict between mu naughts and magnetic moments. And so we're glad we don't have mu naughts here. The energy shifts, as you see, depend on the J, L, and I quantum numbers. The I, of course, is just the spin of the nucleus, but the J and the L are quantum numbers of the electronic basis state that we're looking at, the one that's being perturbed. What is F? Well, F is the quantum number of the total angular momentum, and what is that? Well, that comes from combining J tensor product with I. So for example, if we took the most interesting case here in the case of hydrogen, the most interesting level for the hyperfine structure is the ground state. The ground state in the fine structure notation is a 1s 1/2, where this of course stands for S stands for L equals 0, and the 1/2 stands for J equals 1/2. This is because 0 crossed with 1/2 equals 1/2. That's where you get J like this. This is L crossed with S, you see, equals J. So we have J equals 1/2. So in the 1s 1/2 level of our unperturbed system, J crossed with I turns into 1/2 crossed with 1/2, which is therefore equal to 0 or 1. So there are two F values, F equals 0 and F equals 1. And because the energy has this FF plus 1 here, you can see it's an increasing function of F. And so what this means is that the 1s 1/2 level in the unperturbed system, meaning the full fine structure, even including the Lamb shift, that's what we have here. When you turn on the perturbation, it splits like this, and you have an F equals 1 and an F equals 0 level. These are the two hyperfine levels. So the ground state of hydrogen, which by the way was fourfold degenerate because the two electron states spin up and spin down, and the two proton states spin up and spin down. By the way, this 1/2 here for I means I'm talking about a proton. We could also talk about deuterium, where you have a deuteron, where you have a deuteron as a nucleus. That's a different story. But for ordinary hydrogen, there's the nominal ground state from the fine structure model, even if you throw in the Lamb shift, is fourfold degenerate. 2 for the electron spin up and spin down, and 2 for the nucleus. But when we turn on the hyperfine effects, this splits into two levels, and F equals 0 and F equals 1. The F equals 0 is a singlet, it's non-degenerate, and F equals 1 is threefold degenerate. The degeneracy you see is 2F plus 1 because of the magnetic quantum numbers for M sub F. So therefore, the actual ground state of the hydrogen atom, and this is the real ground state of the hydrogen atom now, is actually the F equals 0 hyperfine level, which is genuinely non-degenerate. But slightly above that, a shift in energy is an F equals 1 state. And this is a long way away from the N equals 2 states, which are way up there on this energy scale. By evaluating this formula for F equals 1 and F equals 0 and subtracting, we get the energy difference between these two. And this energy difference, if you measure it in wavelength units, is 21 centimeters. In frequency units, it's about a gigahertz in frequency units, something like that. Now, we're obviously talking about the gnat's eyebrow in the analysis of hydrogen. We've gone through one correction after another, each one smaller than the previous one. Fine structure, Lamb shift, and now hyperfine structure. And you may wonder if we're wasting a lot of time on tiny, tiny effects that are not important. While these effects may be tiny, but in fact they are quite important in practice. Two applications of this splitting. One of them is in astrophysics. The hyperfine splitting in the ground state of hydrogen is this 21 centimeter line, which is important in radio astronomy. It arises when you have clouds of hydrogen atoms. By the way, there's a story about why you have clouds of hydrogen atoms. If you have a bottle of hydrogen gas in a laboratory, it's not atoms at all, it's molecules, it's H2 molecules. And this analysis that I've just gone through doesn't apply to a molecule, it applies to the hydrogen atom. It's a totally different story for the molecule. However, out in the galaxy, depends on the situation, but out in space, the density is so low that in order to, the thermal equilibrium requires that the hydrogen molecules split up into hydrogen atoms, which they do. So you have large clouds in galaxies of hydrogen atoms. And these are frequently exposed to ultraviolet radiation from nearby stars. And what that does is it causes excitation so that the F=1 levels are populated. Sorry, the F=0 levels, there's an equilibrium between them, transitions back and forth. And so what you get is that every so often an F=1 level emits a photon and drops down into the F=0 level. That photon has a wavelength of 21 centimeters, and that means that these gas clouds radiate at that frequency. So this is a big deal in radio astronomy because it allows you to track these gas clouds of hydrogen. There's all kinds of things you can do with them. Looking at Doppler shift, you can get the velocity of the clouds. You can get information on the thickness of them, on their temperature. There's research going on nowadays regarding the early universe, and the 21 centimeter line is playing a big role in that. Earlier, before major galaxies formed. All right. Anyway, so that's one application. Another application of hyperfine structure is in atomic clocks. Atomic clocks aren't usually based on hydrogen, although they could be if you wanted to. People have built atomic clocks on hydrogen. Usually they use cesium. The story with cesium is a little more complicated because the spin of the nucleus is 7 halves. And because being an alkali atom, we don't have analytic formulas for 1 over r cubed like we do for hydrogen. You have to do it numerically using the estimates for the wave functions. But otherwise, the story goes through in a rather similar way. For cesium, you have a F equals not 0 and 1, but rather 3 and 4 in the case of cesium. And it's the transition between the hyperfine F=3 and F=4 levels of cesium, which is used to, currently it's the standard for defining the second, because it can be measured to such high precision. So these hyperfine effects are quite important in practice. I don't know if any of you ever saw the movie Contact with Jodie Foster. It's kind of dated now. If you see it, it's really, I mean the 2020s are looking to be so miserable compared to earlier decades that they're so naive. It's hard to believe what people thought back in those days. But anyway, it was a Carl Sagan kind of a movie. And anyway, if you saw it, then what you know is that the aliens communicated with us on the 21 centimeter line because they knew we'd be listening at that frequency. And they sent out sequences of prime numbers to prove that they were intelligent, because galaxies won't do that. Actually, it wasn't the 21 centimeter line. I think they doubled the frequency because there's too much noise at the at the 21 centimeter line. Anyway, that's what they did in the movie. So this has a lot of impact, including on Hollywood. Let's see. I think that's all I want to say. So if it is, that means it's the end of the semester, and I finished it with 3 minutes to spare. So are there any questions then about this? No questions about it. You know, the last couple of nights I've been getting no questions, and then I shut things down and people start to go home, and then somebody comes up and asks a question. If you have a question, ask it now so everybody can hear it. A lot of people were interested in questions from other people. Any questions? back when we used to have in-class classrooms, I always brought in pizza for everyone in the last lecture. It was partly a bribe to make people give me good teaching evaluations. But anyway, I'm sorry I can't give you pizza tonight. If we, I don't know whether we're going to be back into in-class lectures by the end of next semester. We don't know. But if we do, I promise you pizza then, okay? Okay, good. All right. So that's all then. And good luck with everything. By the way, about the exam, so I sent out emails. If you didn't get the email, let me know because I tried to send it to everyone about the exam. It gives you the basic information. There's more on the website. Next week, of course, is Dead Week. I'm going to hold regular office hours tomorrow and also on Friday of Dead Week. And if you've got something urgent during Dead Week you want to ask me about, send me an email and I'll answer you as quickly as I can. Otherwise, the exam will be on Tuesday of exam week. It'll last 2 days. You get 2 days to do a kind of a take home. It's definitely a take home exam, but it'll be kind of like a last homework problem. All right, I think that's all I can think of. If there's no more questions, let me get out of share screen. And no more questions. Last chance. Okay, here I'm going to pause the